Okay, so in the last lecture, we tried to understand the concept of magnetic permeability. We tried to understand what magnetic susceptibility means. We tried to understand what diamagnetic material or paramagnetic materials relative permeability actually is, and we talked a little bit about the magnetic behavior of certain type of materials. Now the topic for today is magnetic hysteresis of ferromagnetic materials. Like we talked about earlier, we said that the ferromagnetic materials are different than diamagnetic and paramagnetic materials. They are far more stronger magnetic materials as compared to diamagnetic and paramagnetic materials, but along with that they behave very differently from dia and paramagnetic materials. In this lecture we will try to understand why the ferromagnetic materials uh, behave differently than diamagnetic or paramagnetic materials. So the topic for today is going to be magnetic hysteresis of ferromagnetic materials. So as an example of these materials, he's saying that these materials include iron, nickel, cobalt, and according to the experiences that we have had in the past or from the childhood, we know that these materials, iron, nickel, and cobalt, they exhibit strong magnetic properties due to the fact that their magnetic dipole moment align readily along the direction of external magnetic field that is applied to them. Such materials not only remain align themselves very easily, very readily to the external magnetic field, but in addition such materials also remain partially magnetized even after we remove the external magnetic field. Because of this, whenever we remove the external magnetic field, if those domains, if those atoms, if those magnetic moments are still aligned in some way, as a result all those magnetic moments, instead of canceling each other, they will add up and give us a value of m, and as a result that material will now exhibit the properties of a magnet, and as a result uh, it will act as a magnet. We will use that material as a permanent magnet. So he's saying that because of this, such materials, because of this property of uh, remaining some of that material partially magnetized even after the external magnetic field is removed, that makes these materials very useful to us uh, if we want to manufacture permanent magnets. So in order to understand what a ferromagnetic material is or how the ferromagnetic material behaves, we need to understand the concept of magnetized domains. Basically, we talked about magnetic moment of electron, then we said that all the vector sum of that magnetic moments in an atom, when we add those up, we'll get a value for magnetic moment of an atom, the cumulative magnetic moment of a single atom. Now, what is a magnetized domain? A magnetized domain of a material is a microscopic region which is of the order of 10 raised to power minus 10 cubic meters. So small that the volume of that region will be of the order of 10 raised to power minus 10. And in that microscopic region, the magnetic moments of all its atoms, which are roughly 10 raised to power 19 atoms, they are aligned parallel to each other. What he's saying is that we have taken a small quantity, a small volume, and this volume is of the order of 10 raised to power minus 10 meter cube. It's so small, and this volume roughly contains 10 raised to power 19 atoms. And in this volume, all these atoms have some magnetic moments, and these magnetic moments of all these 10 raised power 19 atoms, they are aligned in the same direction. So all the magnetic moments are parallel to each other for this 10 raised power 19 atoms in this domain. So we'll say that this type of division, this type of part, this type of a region will be called magnetized domain. Why? Because the magnetic moments of 10 raised power 19 atoms are in the same direction. They are parallel to each other. This permanent alignment is attributed to strong coupling forces between spin magnetic moments constituting an individual domain. In the absence of any external magnetic field, the domains take random orientation. Just like atoms we talked about earlier, he's saying that if these are domains, I will not be able to draw all these domains. There are so much of them. He's saying that in the absence of any external magnetic field, uh, all these domains will be randomly placed, and as a result they will cancel each other out, and as a result the total magnetization will be zero. But also, before we say talk about something else, he's talking about domain walls. This boundary, he's calling it domain walls. He's saying what domain walls are. Boundaries between the two domains consist of the thin transitional regions, thin regions after which the domains or the atoms change their direction to some other direction. Is basically as this that thin part is called domain walls. And magnetized sample, if we want to know how a ferromagnetic material works, he says that whenever we place an unmagnetized sample just like this, in which the domains are randomly aligned and as a result the total magnetization is zero, he's saying that in that scenario, will place such an magnetized sample into any external magnetic field. As a result, those domains will start to align themselves according to the externally applied magnetic force. So if they were in this position, if we apply an external magnetic field, these domains will both of these domains will try to align themselves according to the externally applied magnetic field. So he's saying that the quantitative understanding of how they are formed, that uh, basically corresponds to quantum mechanics, and that is outside the scope of this course. The main goal behind we studying these things is for us to understand why paramagnetic behave in a certain way, and in order to understand that, only a quantitative description of magnetization process will be enough for us to understand how this thing is behaving. We don't need to quantify that relationship. So if we want to uh, get an idea of the magnetization behavior of a ferromagnetic material, all we need is uh, a thing, an equipment, which from which we can calculate the value of H that we are applying, the magnetic field intensity that we are applying externally, and the value of B, the magnetic flux that is present inside a material. If we have such equipment which measures the value of H, magnetic field intensity, that we applied externally, and the value of B is basically the magnetic flux density which is present now inside the material itself. If we have the equipment to calculate these two things, we can easily get an idea about the behavior of ferromagnetic material. So let's suppose that we have such a equipment, and we increase the value of we give the value of magnetic field intensity H, and we measure the corresponding value of B that we get inside that material. So we know that the value of B will be mu naught M plus mu naught H. So this M will be due to the alignment of the domains, and this H will be due to the externally applied uh, magnetic field intensity. So he's saying that let's suppose we have taken a piece of iron and we have the capability to measure the value of B and H, and we have started from an unmagnetized state of that iron, and we uh, drew this to be O. O is basically the point at which the value of B and value of H is 0. So you need to know that B is this. B corresponds to the magnetic flux density of that material, and H is the magnetic field intensity that we are providing externally. So he's saying that as we start to increase, if we say that we have just like this. If we say that we have H here and we have B here, he says that if we start to increase the value of H, the value of B will begin to rise, as we have talked about earlier. So it will be a linear relationship until. Why is the value of B rising? Because as we are increasing the value of magnetic field intensity, the more and more domains are aligning themselves according to this magnetic field intensity, and as a result, this B is increasing. But there will come a point at which there are no more domains to align. And for that case, whenever we increase the value of H, the value of B will not increase. And as a result, we'll get this knee. Okay, so we have this knee. Now the value, even by increasing the value of H, the value of B is not increasing that much. So this is the saturation. This is the region at which all the material has run out of domains to align, you can say this. Okay, so he's saying that we've reached here. Now the material is magnetized. Once we reach here, he's saying that when we try to or when we drop the value of this H, for example, it was here. Now we started decreasing this value of H, and when we started decreasing this value of H, the corresponding value of B will not follow the same path. Even when the value of H is 0, there will be some kind of magnetic flux still present in that material. That magnetic flux which is present in that material is due to this M, is due to those aligned magnetic domains which have not randomized yet. So we said that once they are aligned, some of them will remain partially magnetized, and that magnetic flux which is now present in the absence of any external magnetic flux, that magnetic flux has a name. This amount of magnetic flux will be called a residual flux. Okay, so you can relate to its name. This is the residual flux. Now if we start increasing the value of H in the opposite direction, then the value of B will start to decrease. Okay, so there will come a point at which the value of B will now become 0. And when we keep on increasing the value of H to opposite direction, what's happening is that we are forcing these domains to misalign themselves whenever we are applying the value of H in opposite direction. So we're forcing these domains to change their direction, to change their alignment. So there will come a point at which the value will of B will become 0, and if we keep on increasing the value of H, this will follow the same path, and the B will start to increase in that direction until it reaches the saturation point. Now the domains are once again saturated, but now they are in the opposite direction. If we start decreasing H again, then there will be the same kind of attitude. Even when the value of H is 0, there will be some residual flux, And if we start increasing this again, we'll have this, and then we'll have this. So this type of loop is basically what we get. He's saying that once the material is magnetized, it will never cross this point, this zero, at which the value of B as well as the value of H is zero. Okay, so this behavior of ferromagnetic material is basically called hysteresis. The literal meaning of the term hysteresis is lag behind. If you take a look at this thing right here, you'll see that uh, when we started, H and B were in phase. None of them was lagging behind. Once this saturation region started, the B starts to lag behind. After that, when we started to decrease the value of H, the value of B was lagging once again. It was not decreasing the same way in which the value of H was decreasing. When the value of H was 0, B still had some values. When the value of H was in negative, the value of B still had some positive values. Once again, at this point, the value of H was negative and the value of B was 0. And once we surpassed this point, then the value of B started to be negative. So the value of B was lagging behind. So that's why this process is called magnetic hysteresis. Basically, the magnetic flux density is lagging behind, and this loop that we have drawn here, it is called hysteresis loop. This is the magnetization process in ferromagnetic material. Okay, so the specific shape and the extent of hysteresis loop depends on the properties of the material and on peak to peak range. This loop will tell us what type of ferromagnetic material we're talking about. It means that if this loop is wide, okay, if this loop is wide, then we will say that this is a hard ferromagnetic material. Hard ferromagnetic material means that it is not easy to misalign its domain. Hard ferromagnetic material means that it will take a lot of effort to demagnetize and then remagnetize that material. It means that the hysteresis loss will be larger in such materials if that materials need to be magnetized and demagnetized several times in a second, just like in a transformer. In a transformer, the core needs to be magnetized and demagnetized 50 times in a second, almost 100 times in a second. Okay, so he's saying that uh, in hard magnetic materials, in those magnetic materials in which the hysteresis loop is wide, uh, more work will need to be done in order to demagnetize and remagnetize that material. It means that the application of this material will be in the manufacturing of permanent magnets, that once these materials are magnetized, it is very difficult for us to demagnetize that material. We have to spend a lot of energy in order to demagnetize those materials. That means that these are the perfect uh, material if we want to make a permanent magnet, or the magnets that we don't want uh, to, what we'll say about that, to lose their potency with respect to time. So the white magnetic materials are hard ferromagnetic materials, and the magnetic materials in which this hysteresis loop is narrower, very narrower, such type of magnetic materials will be best to be placed in the cores of transformers, in which we have to magnetize and demagnetize and remagnetize that core several times, and we want as less energy expenditure for this process as possible. So for that materials, the hysteresis loop will have to be narrower, and we will call those materials to be soft ferromagnetic materials. So these were the things about magnetic hysteresis of ferromagnetic materials. The next thing on our agenda is magnetic boundary conditions. Now we know that we have studied already the magnetic boundary, the electric boundary conditions. So magnetic boundary conditions are not that much hard to understand. We will talk about uh, one magnetic boundary condition today, and we'll talk about the tangential in the next lecture. All we'll do here is that we'll compare the magnetic boundary to the electric boundary, and we'll figure out how the magnetic field will behave on a boundary when compared to the electric field. So he says that we derived the electric boundary conditions to be d1n minus d2n for normal components to be rho s by using this property, which was d dot ds Gauss's law is equals to q. And if we compare this to magnetostatics, the Gauss's law for magnetostatics is b dot ds is equals to 0 for closed surface integral. So if we compare this, we can say that b1's normal component should be mentioned like this. So we'll say that b1's normal component will be equals to b uh, like this. b1n should be equals to minus bn, just like this. And in this case, what this thing physically means is that the normal component of magnetic field density, magnetic flux density, will be continuous across the boundary. So if this is the boundary, and we're talking about b, this is the normal component of medium 2, this is medium 1. We say that this is b2n, this is b2t, this is b1n, this is b1t. So he's saying that this b1n and this b2n, they will be the same. Okay, so if we want to convert it in the form of magnetic field intensity, what we can do is that we can say that this is mu 1 h1n and this is mu 2 h2n. As we know that these are two different mediums, so this will mu 2, and this will be the magnetic permeability of the above material will be mu 2, and the material beneath the boundary will be mu 1. So we can say that this is how we can mention this boundary condition in the form of magnetic field intensity. So he's saying that we have a single boundary condition in which the normal component of the magnetic flux density is continuous. So if we compare these two, the electrostatics and magnetostatics, we can say that the normal component of B is constant, is continuous across the boundary, but the normal component of D was not. We can see this from this equation that the normal component of D was not continuous across the boundary if there is a surface charge density that was present on the boundary itself. But the magnetic in case of magnetic flux density, the normal components are continuous across the boundary. So these two things are in contrast. Okay, the magnetic field is behaving in an opposite way as compared to the electric field. So he says that similar reversal applies to the tangential component of electric and magnetic field E and H. How? He's saying that the tangential component of E is continuous across the boundary. We knew that the tangential component of the first electric boundary condition was E1t is equals to E2t, if you can remember. He's saying that the tangential component of E was continuous across the boundary, but as this reversal, if we extrapolate this reversal to magnetic field, we can say that the tangential component of magnetic field intensity will not be continuous. It cannot be continuous, may not be continuous if we have a current density present at this boundary condition. So I hope you know what I'm talking about. I'm talking about the reversal of roles here. He was saying that in electric flux, uh, in electric boundary conditions, the normal component of electric flux was not continuous and it was dependent on the charge that was placed at the boundary. If that charge was zero, that normal component would have been continuous too. And similarly, he's saying that in magnetostatics case, the same thing will happen, but it will happen to the tangential component. He is saying that now the tangential component of the magnetic field will not be continuous if there is some sort of current density that is present uh, across the boundary. So let's suppose that we have this boundary and different we have a current density at this point, and the direction of current is, these are dots. So I know you can't see them here, but these are dots. Okay, this means that the current is coming out of the screen. So he's saying that if this is b1 h1, similarly h1 and b1, they will, both of them will be in the same direction. He is saying that if we want to know what the value of normal or tangential component in this case will be, so how can we measure that? We will use Ampere's law, and in order to use Ampere's law, we need to imagine a contour. So he is imagining a contour in the form of a rectangle, because we're talking about tangential component. So we need to have uh, such sides which are in parallel or anti-parallel, so that we can easily calculate the value of h dot dl. So we'll take the value of we'll take the direction of contour to be in counterclockwise direction by right hand tool, placing our thumb in the direction of current, and the fingers will give us the direction of h. So this is the direction of contour. So if we want to calculate the value of h dot dl by using Ampere's law, what we'll need to do is we'll need to segregate this contour into its different parts. But we, as we did back in electric boundary condition, will suppose that these two sides are very very small, because we need to take into account the boundary as compared to these sides. As a result, the only two segments that will be of value to us will be a to b. This is a, this is b, this is c, this is d, and h dot dl plus c to d and h dot dl. We have ignored these two segments. Okay, so this will be equals to I. He's saying that obviously a to b, there will be, for a to b, okay, there is a little discrepancy. In the book he has taken the bottom one to be second, so we'll change it accordingly so that you do not get confused. So this is m1. So he's saying that for a to b, this is h2 dot dl, and for c to d, this is h1 dot dl. Okay, he's saying that h1 is in media 1, h2 is in media 2, I is the net current passing through dl, h2 is basically parallel to ab, h2 is parallel to h2t is parallel to ab, and h1t is anti-parallel to cd. So we can say that h2t delta l, if delta l is the length of this side, h2t delta l minus h1t delta l, that should be equals to I. And we want to cancel this delta l out, so we'll change this by js delta l. We know that we can write this as js delta l. So Js delta L, this delta L will cancel each other out, and as a result we'll get H2T minus H1T is equals to Js. So this is basically the second boundary condition for magnetism. This is the second boundary condition for magnetism. If you compare these two equations, you'll see that they are pretty much similar. We have Js in place of rho s, and we have H2T and we have H1T. The only thing that is different is the normal components and the minus sign. He's saying that the surface current can exist only on the we know that the surface current can exist only on the surface of the perfect conductors. Interfaces between the media with finite conductivities Js will be 0. So at that point, if the value of Js is 0, H2T will be equals to H1T. In this case, when Js, then when there is no current on the boundary of this surface, then the tangential component will also be continuous, just like the normal component. So these are the two magnetic boundary conditions. There is a possibility that you might feel confused in this. If you do feel confused, you are very welcome to ask your queries in the interactive session. Please do not keep your questions in your minds. I understand this might feel a little bit confusing to you, so please discuss whatever concerns you the most. This is it for today. We'll talk about inductance in the next lecture. Thank you for listening.